Noche Cósmica.
Every morning, 8 minutes and 20 seconds before you see the sun break the horizon, it has already risen. Light travels at 300,000 kilometers per second, yet it still takes those 8 minutes to cross the void between our star and this world. In that gap between the sun's actual position and where we perceive it in the sky, there is something quite profound, a delay so perfect and constant that we never notice it at all. This thought alone carries us gently toward a question that has occupied the minds of physicists, philosophers, and dreamers for centuries. What if that light never came? What if, one morning, the sun did not simply pause behind a clouded horizon, but dimmed entirely? What if the most reliable source of energy in our existence, the furnace that has burned steadily for 4.5 billion years, simply stopped? This is not a prediction. This is not something we need to fear in any practical sense, but it is worth exploring. If you find yourself drawn to these quieter corridors of thought, to the strange beauty of what-if scenarios that play out across the cosmos, then I'd like to invite you to subscribe. Here, we journey through the deep questions of space and time together, moving slowly through the scenarios that reveal how perfectly balanced our existence truly is. There will be many more nights like this one, but for now, let us begin where all things begin. Let us begin with the light. Picture the moment just before dawn. You are standing in some quiet place, perhaps near water, perhaps surrounded by trees, perhaps simply in an open field where the horizon stretches unbroken. The sky above is still dark. Stars hang in their familiar patterns. The air carries that particular coolness of the pre-dawn hours, the kind of chill that seems to come from the earth itself, as though the planet has spent the entire night radiating its warmth away into the void. And then, without sound, without announcement, the eastern sky begins to change. It is not a sudden transformation. The process is so gradual that if you were watching continuously, you might miss the precise moment when darkness tips into light. But the quality of the sky shifts. A deep indigo touches the horizon. Clouds, if there are any, pick up the faintest blush of color, first purples, then oranges, then finally the deep gold of true morning light. The stars begin to fade. The world that was hidden in darkness slowly reveals itself. Trees become visible first as shapes, then as individual forms. The grass beneath your feet, which was only an idea moments before, becomes green again. The texture of bark becomes apparent. Details return. Color returns. The entire visible world reconstructs itself from the darkness in the span of just a few minutes. What we are witnessing is something so familiar that we rarely think about it at all. We have seen this sunrise thousands of times. We have taken for granted the reliability of its return. Day follows night. Night follows day. The sun rises. The sun sets. This rhythm has defined every moment of human life, shaped every culture, structured every calendar, organized every civilization. It is the most fundamental pattern of existence. But think for a moment about what you are actually seeing in that pre-dawn sky. You are not seeing the sun itself rising. You are seeing the light it cast 8 minutes and 20 seconds ago, traveling through the vacuum of space at the fastest speed anything can travel, finally reaching your eyes. The sun is not at the horizon. The sun is already substantially higher in the sky, but its light has not yet arrived at this location where you stand. This delay is imperceptible. It is so small that for practical purposes we ignore it. We speak of the sun rising when we see its light, even though the sun itself rose 8 minutes earlier. Our language and our perception have naturally aligned with this convenient fiction. But it is a reminder that there is always a gap between what is and what we perceive. And it is in contemplating this gap, this 8-minute window between the sun's actual state and our knowledge of it, that we can begin to truly understand what the question means. What if the sun went dark? What if, in the vast furnace at the center of our solar system, something catastrophically changed? What if the fusion reactions that have sustained every moment of life on Earth simply ceased? We would not know immediately. For 8 minutes and 20 seconds, the light would continue coming. We would see no change at all. The sunrise would happen normally. The morning would progress as it always does. And then, with a strangeness that would be utterly disorienting, the light would simply end. But we are getting ahead of ourselves. We are standing still in this moment before the sunrise, in this hushed pre-dawn darkness, and we have not yet witnessed the light arrive. Let us stay here a little longer. The sky is beginning to brighten now. The indigo has deepened. Hints of orange are touching the lowest clouds. Birds are stirring, called to alertness not by the sun itself, but by the light that has been traveling since before they were awake. The world is poised on the edge of day. The transition is happening. There is something about this moment, isn't there? Something about the moment before light returns to the world that carries a particular quality of awareness. We stand between darkness and day, between sleep and waking, between the hidden and the revealed. It is a threshold, and thresholds have a power all their own. The sun that created this light was born in chaos. Billions of years ago, in a region of space that held nothing but gas and dust, gravity pulled those scattered particles together. They compressed. They heated. Pressure increased. And at some critical moment, the density and temperature became sufficient for fusion to ignite. Hydrogen began to fuse into helium. A star was born. This star, our sun, has been burning since then. It has burned continuously. It has never faltered, never dimmed, never given any sign of failure. It has burned through the equivalent of 400 million tons of hydrogen every single second. Yet it has enough fuel remaining to burn for another 5 billion years. Its reliability is the foundation upon which all life on Earth has evolved. Every species, every adaptation, every biological strategy has developed assuming that the sun will rise tomorrow, and the day after tomorrow, and the day after that. The horizon is truly orange now. We are moments away from the actual appearance of the sun's disk. The darkness is almost gone. The world is almost entirely visible. In seconds, the sun will break the horizon, and day will fully commence. It is in these final seconds of night, in this moment of highest anticipation, that the question becomes most poignant. What if this did not happen? What if the light did not come? But it does come. The sun breaks the horizon. Its light floods the landscape. The pre-dawn meditation ends. Day begins, and the world, as it always does, turns its face toward the light. What if, one ordinary morning, the sun simply ceased to shine? Not a gradual dimming, not a slow drift into ice age across millennia, but a sudden, complete absence of light and warmth across the entire star that has sustained every living thing on Earth for 4.5 billion years. It is a question that does not belong to the realm of prophecy or dread, but to the deep, quiet territory of thought experiment, a tool that physicists and astronomers have long used to understand how our world is woven together, what dependencies we take for granted, and what would happen if one single thread were pulled. This scenario will not occur. The sun will not go dark tomorrow, or in your lifetime, or in your children's lifetimes. But by walking through this imaginary darkness, we begin to understand something profound about the star we orbit, about the fragility and resilience of life itself, and about the invisible forces that hold our world in balance. It is a thought experiment rooted in real physics, real timescales, and the genuine structure of how stars age, burn, and eventually fade. If you find yourself drawn to these kinds of journeys through space and time, where we explore the hypothetical while learning the actual, consider subscribing. We take many such walks through the cosmos here, gentle, unhurried explorations of what if, grounded always in the science that explains our universe. There is something deeply settling about understanding the systems that hold us, even in imagination. But let us return to our thought experiment. Before we can imagine the sun going dark, we must first understand what the sun actually is. We must picture it not as a simple glowing orb in the sky, but as a vast, turning furnace of nuclear fire, a living, breathing engine of fusion that has been quietly at work since before our planet took its present shape. We must understand its layers, its invisible currents of superheated plasma, the billions of tons of hydrogen it converts to helium every single second, and the remarkable stability that has allowed it to do so, without interruption, for so long. In the stories and mythologies of countless human cultures, the sun represents constancy itself. It rises and sets with such reliable regularity that we have built our lives, our calendars, our very sense of time around its movements. We have forgotten, in our modern age of electric light and climate-controlled spaces, how dependent we truly are on that distant ball of fire. And yet every plant, every animal, every breath of oxygen in your lungs is a gift of that constancy. Every calorie you consume can be traced backward through the food web, or through fossil fuels that once were plants, back to photosynthesis powered by sunlight. What we are about to explore is what would unfold if that constancy were shattered. But here is where we must pause and hold two truths in mind simultaneously. The first is that stars do not simply switch off. There are deep, well-understood laws of physics that govern how stars burn and age. A star cannot go from steady fusion to complete darkness in an instant, any more than a fire can vanish without consuming itself entirely. The sun has structural integrity, gravitational forces holding it together, and fuel reserves that are measured in the billions of years. And yet, and this is the second truth, stars do eventually die. They do exhaust their fuel. They do change and cool and transform into remnants of what they once were. The sun itself will not burn forever. In perhaps 5 billion years, long after humanity as we know it has risen and fallen, long after our civilization has become dust and myth, the sun will swell into a red giant and consume the inner planets entirely. But that is a different story, a different kind of ending. What we are imagining now is not the sun's destined aging, but a sudden catastrophe. So where would such a catastrophe come from? What could possibly cause a sun to go from shining brightly to absolute darkness in the space of moments? There are a few directions that physicists and science fiction writers have explored, each rooted in real astrophysics, but extending into the speculative realm. Perhaps a sudden, catastrophic disruption of the sun's magnetic field, which plays a crucial role in its structure. Perhaps some exotic form of matter or energy that we do not yet fully understand, interacting with the sun in an unexpected way. Perhaps, and we offer this as pure imaginative play, a cosmic collision of such improbable violence that the sun itself was struck and disrupted. These are not predictions. They are not fears we should harbor. They are invitations to our imagination, labeled clearly as such, so that we can use them as a starting point for understanding what would actually happen to Earth in such a scenario. The real physics of cooling, of light travel, of atmospheric change, these become clear only when we ask the question that begins with if. Let us ask it gently now, as we move deeper into the darkness of our thought experiment. The sun is not a mystery to us anymore, though it was once. For millennia, humans watched that golden disk move across the sky and could only imagine what it might be. They told stories. Gods rode in chariots. Fire fell from heaven. Arrows of light pierced the clouds. But the sun, in truth, is something far more elegant and far more strange than any mythology we invented to explain it. and understanding what it truly is makes the thought of its darkness all the more profound. At its heart, the sun is a furnace of such immense power that it holds itself together through the sheer weight of its own gravity, pressing inward with a force almost incomprehensible to the human mind. This inward crushing weight creates conditions so extreme, temperatures so beyond anything we can reproduce on Earth, that the very atoms at the sun's core lose their identity. Hydrogen nuclei are forced so close together, pressed by the weight of all that stellar mass above them, that they begin to fuse. Two nuclei collide and merge into one, and in that fusion, a tiny fragment of mass is converted into energy. It is the most efficient power source the universe has ever created, far more potent than any chemical reaction, any nuclear fission we might engineer in our own reactors. This is nuclear fusion, and it has been the engine of the sun's light for 4.5 billion years. That number is worth sitting with for a moment. 4.5 billion years. Our own species has existed for perhaps 300,000 years. The entire recorded history of human civilization spans barely 5,000 years. And yet the sun has been burning steadily, fusing hydrogen into helium, releasing that incomprehensible energy into space, for a span of time so vast that the history of our entire world is but a brief flicker in its lifetime. The sun was already more than 1 billion years old when the first single-celled organisms appeared in Earth's oceans. It had burned for another 1 billion years before the first plants began to clothe the land, and it has continued its steady fusion long enough to watch our species emerge, build civilizations, and eventually turn to the sky with telescopes and mathematics and ask, what is that star that gives us life? The sun itself is not uniform. Imagine if you could cut through it like an orange, layer upon layer. At the very center lies that fusion core, where temperatures reach nearly 15 million degrees, and where hydrogen is being converted into helium in reactions so violent and so energetic that they would seem impossible if we did not witness their results every day. Around this core is a region called the radiative zone, where the energy released from fusion travels outward, not as light exactly, but as radiation. Photons bounce and scatter through this region, constantly being absorbed and re-emitted, slowly working their way toward the surface. It is a crowded, dense space, where the material is still impossibly hot, still under tremendous pressure, but gradually cooling and thinning as it moves outward. Beyond the radiative zone lies the convective zone, and here the character of the sun changes. The material is cooler now, only 1 million degrees or so, still incomprehensibly hot by any earthly standard. And here the energy from the core begins to move upward, not by radiation, but by convection. Imagine great currents rising and falling, like water boiling in a pot, but on a scale so vast that entire Earths could fit inside these currents. Hot material rises from below, carrying that precious energy with it, and as it reaches the cooler outer regions, it releases that energy and sinks back down. It is a great circulation, perpetual and tireless, and it has been spinning for eons. At the surface of this convection zone lies the photosphere, that visible face of the sun that we see in the sky. It is perhaps 1,000 kilometers thick, and it is here that the light finally escapes. The radiation that was generated 15 million degrees away in the core, that scattered and bounced through the radiative zone, that was carried up through the convective currents, finally breaks free here and travels outward into space. This is the light that has touched every living thing on Earth. This is the light that powers photosynthesis. This is the light that warms our world, and it has been reaching us, faithfully, reliably, for 4.5 billion years. But even the photosphere is not the end of the sun. Beyond it lies the chromosphere, a thin, wispy layer that is ordinarily invisible because it is so faint compared to the brilliant light of the photosphere behind it. Yet, during a total solar eclipse, When the photosphere is blocked by the moon, the chromosphere appears as a thin red line, rimming the sun's silhouette, and what we see is the sun's outer atmosphere. Beyond even that lies the corona, a halo of extremely hot, rarefied gas that seems to contradict everything we know about how heat should work. The surface of the sun, the photosphere, is about 5,500 degrees Kelvin, yet the corona, far above it in the sun's outer atmosphere, reaches temperatures of over 2 million degrees. How can the atmosphere be hotter than the surface? This is one of the sun's remaining mysteries, one that astrophysicists are still working to fully understand, and it speaks to the complexity of what we call a simple star. From the sun constantly flows a stream of charged particles, mostly protons and electrons, a thin wind that escapes the sun's gravity and travels throughout the solar system. This solar wind reaches Earth and beyond, shaping the very space around our planet, interacting with our magnetosphere, creating the auroras that light the high latitudes on clear nights. The sun is not a static furnace contained in one place. It is a dynamic, flowing, radiating presence that reaches out through space and influences everything in its realm. And yet for all this complexity, all this power, and all these layers, and all this constant grinding fusion in its core, the sun is fundamentally reliable. The reactions that power it are not fragile. They are not prone to sudden stops or reversals. Once hydrogen fusion begins in a star, it continues with a remarkable constancy. The sun has burned steadily through the formation of our solar system, through the cooling of Earth's crust, through the emergence of life, through the extinction of the dinosaurs, through the entire rise of human civilization. It has given us light and warmth with extraordinary faithfulness, and because of that faithfulness, we have come to depend upon it in ways so fundamental that we rarely stop to think about it. The sun is simply there. It has always been there. It will always be there, we assume, at least for our lifetimes. But what if that assumption were wrong? What if the sun, this steady furnace that has burned for 4.5 billion years, were to go dark? Now, here lies the peculiar beauty of a star. It is not a light that can simply be extinguished like a candle flame in a sudden gust of wind. The sun will not blink out. This is not poetic sentiment, but rather the consequence of forces so profound that they have sustained our star for 4.5 billion years, and will continue to do so for billions more. To understand why stars do not simply switch off requires us to step into the heart of stellar physics, into a realm where gravity and pressure and heat exist in such perfect, exquisite balance that the system resists sudden change with an almost stubborn persistence. Consider the essential nature of what holds a star together. Gravity, that ancient, patient force, pulls inward with relentless determination from every direction at once. It crushes the sun's material toward its center with such overwhelming force that the pressure and temperature at the core reach incomprehensible extremes. At the sun's heart, hydrogen nuclei are pressed together so violently that they overcome their natural electromagnetic repulsion and fuse into helium. This fusion process releases tremendous energy, which radiates outward as light and heat. But here is the balance. This outward-pushing radiation pressure, born from that same fusion furnace, pushes back against gravity's inward crush. The two forces, gravity squeezing inward, radiation pressure pushing outward, exist in a state of dynamic equilibrium. The sun is a negotiation between destruction and creation, moment after moment, second after second, for billions of years. This equilibrium is remarkably robust. It does not fluctuate wildly. It does not permit sudden shifts. If, hypothetically, the fusion reactions were to slow even slightly, gravity would immediately compress the core more tightly, raising the temperature and pressure until the fusion reactions sped up again. Conversely, if fusion suddenly burned hotter, the resulting radiation pressure would push the outer layers outward, reducing core density and temperature until the reaction rate decreased. The system self-corrects with an elegance that speaks to the deep order underlying the cosmos. Stars are self-regulating furnaces, held in place by the very same forces that might seem destined to tear them apart. This brings us to the question of stellar aging. Stars do change, but only across timescales so vast that human imagination strains to hold them. A typical star like our Sun will burn its hydrogen fuel for roughly 10 billion years. The Sun is currently about halfway through its life. It has already existed for 4.5 billion years, and will continue as it is for another 5 or 6 billion more. This is not a star in its twilight. It is a star in its stable middle age, burning with the quiet confidence of a furnace that has found its rhythm and intends to maintain it. As a star ages and its core becomes gradually enriched with helium ash, the process does accelerate. The core contracts slightly, the temperature rises a fraction, and the hydrogen fusion in the shell surrounding the helium core begins to proceed faster. The star grows somewhat brighter, somewhat larger, but even this aging process unfolds across millions of years, gradual, predictable, governed by the same physical laws that have always governed it. There is no mechanism in stellar physics that permits a sudden shutdown, no switch that flips, no sudden loss of pressure or gravitational catastrophe that would extinguish the light all at once. What, then, might we imagine could disrupt this remarkable equilibrium? In the realm of real physics, there are very few possibilities, and each one is either so improbable that it borders on impossible, or so distant in time that it belongs entirely to the future. A nearby supernova explosion could theoretically send a shockwave through the Sun's outer layers, disturbing the balance momentarily. But such events in our galactic neighborhood are extraordinarily rare, separated by timescales of millions of years or longer. A collision with a rogue star or massive object could disrupt the Sun's structure catastrophically. Yet the probability of such an encounter in our solar system is vanishingly small given the vast distances between stars in our corner of the galaxy. As for fuel exhaustion, that is a real phenomenon, and it will claim our Sun eventually, but it will not happen suddenly. When the Sun finally exhausts its core hydrogen, perhaps in 5 or 6 billion years, it will not flicker out. Instead, it will undergo a profound transformation. The core will contract and heat further, and the outer layers will expand enormously. The Sun will swell into a red giant, growing so large that it will likely consume Mercury, Venus, and perhaps the Earth itself in its expanding envelope. It will become dimmer in some wavelengths, redder in its hue, and far more unstable. But between now and then, between this moment and that catastrophic epoch billions of years hence, the Sun's light will remain steady, its fusion fires burning with the same patient reliability that has warmed our world since life first emerged from Earth's oceans. The improbability of sudden darkness cannot be overstated. A star is not a fragile thing, despite its being made of plasma and light. It is one of the most stable, self-regulating systems in nature, and the Sun in particular is a star of modest, unremarkable properties, a middle-aged, steady furnace that has given no indication whatsoever that it might behave in any way unpredictably. And yet, imagination is a precious thing. We are capable of entertaining scenarios that physics forbids, of asking, what if? Even when the universe whispers no. And in the asking of such impossible questions, we sometimes come to understand the real world more deeply, by contrast, by negation, by exploring the boundaries of what can and cannot be. So let us, for the moment, permit ourselves this thought experiment. Let us imagine that through some mechanism we need not yet fully explain, some exotic physics, some cosmic accident, some disruption so bizarre that the ordinary laws of stellar mechanics bend and break. The sun's fusion reactions simply ceased. What then? What would happen to a world that suddenly lost its star? And yet, for all this certainty, for all the physics that anchors the sun to its patient burning, there exists a strange corner of thought where we might ask, what if, somehow, the ancient fires dimmed not in billions of years, but now? What if something interrupted the great fusion engine at its core? The answer, of course, is that nothing reasonably could. But to imagine the unlikely, to sit with hypothetical triggers that exist more in the realm of theoretical physics or science fiction than in any credible astrophysical model, is to deepen our understanding of how impossibly stable our star really is. Consider for a moment the sun's magnetic field. We know it exists. We know it churns and shifts with the solar cycle, that it sculpts the corona into loops and arches of plasma, that it drives the solar wind outward into the dark. What if, in some unimaginably rare cosmic accident, the magnetic field that sustains the sun's internal dynamo were to catastrophically collapse? The sun's rotation and the movement of charged plasma within it generate this field continuously, a self-sustaining loop that has persisted since the sun's birth. A total collapse would require an intervention so severe, so contrary to the known laws of magnetohydrodynamics, that it borders on pure fiction. Yet, if one were to happen, the sun's outer layers would lose the magnetic scaffolding that shapes its behavior. The stellar wind would falter. The sun's visible light would not cease, but its character would change in subtle, profound ways. This remains, of course, purely imaginative. It has never been observed in any star in our galaxy, nor would we expect it to be. Then there is the stranger territory still, the realm where exotic physics meets speculation. What if some form of exotic matter, hypothetical and never confirmed, passed through the sun's core? Certain theoretical frameworks in particle physics suggest possibilities that exist at the very boundary of knowledge, matter that might interact with ordinary atoms in ways we have never encountered, that might, if the conditions were precisely, impossibly right, drain energy from a fusion reaction. Dark matter, that shadowy substance that comprises most of the matter in the universe, surrounds and permeates the sun as it does all stars, yet it passes through, indifferent, invisible, taking no part in the nuclear dance. But what if a concentration of it accumulated at the sun's heart? What if its gravitational effect, or some undiscovered interaction, somehow suppressed the fusion process? Here we venture into territory where physicists themselves would smile gently and say, "This is not predicted, not expected, not within the known framework." Yet it illustrates something profound, that even our most exotic theoretical extensions do not furnish a plausible mechanism for stellar dimming. The absence of such mechanisms is itself remarkable. And then there is simple, honest fiction. Imagine a solar flare so massive, so violent in its magnetic restructuring, that for a brief interval, days perhaps or weeks, the sun's photosphere became obscured by an ejection of material so dense and widespread that it dimmed the light reaching Earth by a fraction too significant to ignore. This would be unprecedented. The largest coronal mass ejections we have ever observed would pale beside it. Yet it remains the most physically grounded of imaginative scenarios. The sun's surface is a restless place, violent and dynamic at small scales. What if that violence, through some cascade of events, amplified to scales we have never witnessed? The sun would still be fusing hydrogen, the light would still be traveling, but between the furnace and us, a veil of the sun's own material would hang in space, dimming but not extinguishing. Within months or years, solar wind would push the veil away, and the full light would return. Consider too, if you will, the quieter possibility, not a catastrophe, but a gradual dimming, as if the sun's fusion rate, regulated by the delicate balance of pressure and gravity, were to slip into a state of temporary decline. This occurs, we know, across the solar cycle. The sun's output varies by tiny fractions of a percent over 11-year periods. What if that cycle extended? What if, over decades rather than years, the sun's luminosity declined by 10%, then 15%? The physics that would govern such a change remains obscure, troubling even to speculate upon. Yet it illustrates that the sun's stability, while nearly absolute in our everyday reckoning, is not infinite. It is balanced, it is maintained, and balance, in this universe, is always subject to disruption, even if the odds against disruption are so astronomical as to render the discussion almost philosophical. These are imaginings. Gentle as they are, they do not contradict what we know of stellar physics. Rather, they exist in the margins, where knowledge gives way to creative thought. In imagining how the sun might dim, we are not predicting its future. We are, instead, mapping the boundaries of the possible, and in doing so, we come to understand that the sun's persistent, reliable light is not a given, not a law of nature, but a remarkable and specific gift arising from a particular star, burning with a particular steadiness in this particular moment in cosmic time. The light that touches your face each morning, that has touched the faces of all who ever lived, it is the result not of inevitability, but of an improbable and beautiful alignment of physics that has held, without interruption, for 4.5 billion years. In the moment the sun's fusion truly ceased, in that singular instant when the last photon escaped the core and began its outward journey through the layers of plasma and gas, nothing on Earth would yet know it. Not your eyes, not the birds beginning their dawn chorus, not the instruments measuring solar radiation. There would be, instead, a peculiar and eerie silence in the universe, a gap between catastrophe and knowledge. Light travels at 300,000 kilometers per second, the fastest thing we know. It is, paradoxically, both impossibly swift and terribly, terribly slow when measured against the vastness between our world and that burning sphere we orbit. The sun sits 93 million miles away. That distance, so incomprehensibly vast that it barely registers in our everyday thinking, suddenly becomes profound. It becomes a delay, 8 minutes and 20 seconds. That is the length of the interval, the time it would take for the information of darkness to reach us. For 8 minutes after the sun's death, the sun would still be shining. Imagine that strange phenomenon. Imagine the contradiction of it. The star is already extinguished, its fusion halted, its light no longer being created, and yet, on Earth, it continues to climb in the sky, as it always does. The dawn breaks as it always has. The soft orange light stretches across the horizon. The morning is proceeding exactly as it always proceeds. A child waking up sees the familiar warm glow through the bedroom window. A gardener steps outside into the gentle early heat. For those 8 minutes and 20 seconds, the world is utterly unaware that something catastrophic has already occurred. What an extraordinary thing to contemplate. During those minutes, nothing in the physical world would change. The light flooding down would remain constant, because it was already in transit. The solar wind, that stream of charged particles flowing outward from the sun, would still be buffeting Earth's magnetosphere, still creating the aurora borealis across the high latitudes, still protecting the upper atmosphere from the deepest cosmic rays. The ground beneath your feet would retain its warmth. The plants in the forest would continue the delicate chemistry of photosynthesis, their leaves still converting sunlight into sugar and energy. No creature on Earth would feel any different. And then, at 8 minutes and 20 seconds after that moment of extinguishment, the light would arrive at the edge of Earth's orbit. The sun's photons, having traveled that enormous distance in perfect, unwavering straight lines, would make contact with the outermost reaches of Earth's atmosphere. For perhaps a fraction of a second, nothing visible would occur. The transition would be so rapid, so absolute, that it might be difficult to perceive unless you were looking directly at the sun itself. The sun would begin to dim, not gradually, as you might imagine a sunset, with colors bleeding across the sky over the course of an hour. No, instead, it would be as though someone had drawn a curtain across it. The daylight would not fade so much as cease. In the course of minutes, perhaps 5 or 6 at most, the sun's disk would blacken entirely. The brightness would drain from the sky. For anyone on the day side of Earth, staring upward in that moment, it would appear as though an eclipse were occurring, but faster, and without the moon. The corona might even become visible for a moment, that ghostly halo of plasma that normally hides in the sun's glare. The sensory experience of those 8 minutes while the light still shone would remain one of the cruelest paradoxes. A person might stand in the morning warmth, completely unaware that they were experiencing the last sunrise of the era of light. A farmer might look out at fields bathed in golden rays, thinking about the crops that would soon be growing, planning a season that would never come. An astronomer might be finishing her overnight observations, preparing to rest before the sun came up, not knowing that the sun's death had already been sealed. The sun would still be rising. That is the weight of distance. That is what 8 minutes means when measured in light years across the void. And somewhere in those 8 minutes, depending on where you stood, the world would be transitioning from night into day, that slow creep of blue spreading across the eastern horizon, the birds beginning their songs, the insects beginning to stir. Some parts of Earth would be in that twilight, that soft purple time before dawn. Other regions would be fully lit, moving through the middle of their day, the sun high and bright in the sky. The Terminator line, that slow-moving boundary between day and night that circles the planet every 24 hours, would be advancing at its usual pace, completely indifferent to what was happening in the vast furnace it illuminated. The delay is not unique to light from the sun. All information across space is bound by this same speed limit. Gravity travels at light speed. Electromagnetic radiation travels at light speed. Radio signals, X-rays, the subtle fluctuations of the solar wind, all of it takes 8 minutes and 20 seconds to reach us from the sun. In that sense, we are always looking at the sun as it was 8 minutes and 20 seconds ago. We are all, in a way, living in the past when we observe the sun at all. But we do not usually think of it that way, because the sun changes so slowly, because 8 minutes is such a minute fraction of the sun's existence that it might as well be the present moment. What would happen to that vast conveyor belt of energy flowing toward Earth during those 8 minutes? The photons that had already left the sun would continue on their course, undisturbed, as if nothing had changed. The solar wind would continue to flow because the particles composing it had already been ejected into space before the sun's light ceased. The heat that had already been radiated outward would keep traveling. But nothing new would be leaving the sun. No new photons would be created. No new particles would be ejected. The sun would be sending nothing into the universe anymore. And from Earth's perspective, during those 8 minutes, we would have no idea. Now imagine the moment the light dies. Not gradually, as the sun will truly dim in billions of years, but instantaneously, as our thought experiment demands. In that first instant, the moment the sun's fusion ceases, the photons that have been traveling outward for 8 minutes have already been accounted for. They are already on their way. The day side of Earth, the side facing our star, continues to glow for those 8 minutes of grace we discussed, unaware that the furnace has gone cold. And so we arrive at the first hour, that strange and harrowing dawn of a darkened world. At the moment of true darkness, the Terminator line, that delicate boundary between day and night that circles our planet every 24 hours, begins its ordinary rotation. Somewhere, it is noon. Directly beneath the sun's absent gaze, the sky remains bright. The shadows are still sharp. People are still stepping out of their doorways to fetch something from their cars, still glancing up at what seems like a perfectly normal day. The clouds catch light as they always do. The warmth still radiates from the ground, accumulated heat from hours of earlier sunshine, still rising as it has for billions of years. There is nothing yet to suggest that the universe has fundamentally changed. But 8 minutes later, that grace period ends. The Terminator line sweeps onward, and as it carries the boundary of day and night around the rotating Earth, something impossible begins to register. The light does not return. The sun should be climbing higher or remaining at its zenith or beginning its descent toward the western horizon, depending on the latitude and the hour. But the sun does not behave as expected. The sun does not exist. Imagine the experience of a person standing in broad daylight. Perhaps it is early afternoon in what would have been Central Europe or the eastern United States or the Australian outback. The morning has been clear and bright. Shadows have been cast by buildings and trees and human bodies, sharp and dark against the pavement and grass. And then, across a span of perhaps 30 seconds to a minute, the light begins to fail. Not like a cloud passing overhead. There are no clouds. The sky was clear. Not like the steady dimming of dusk. This is far too rapid, too complete. The light does not fade from the edges inward. It simply empties from the sky like water draining from a basin. The first reaction, almost certainly, would be confusion. What cloud is this? What weather pattern has emerged so suddenly? People would look up, trying to locate the sun, their eyes searching the now graying zenith. They would not immediately understand that they are searching for something that no longer exists. Some might think of an eclipse, others might feel a sudden, undefined anxiety, a primal wrongness that their conscious minds have not yet caught up to. The temperature would not drop noticeably at first. The ground, the buildings, the air itself, all still carries the heat of hours of sunlight, but the light itself is simply gone. And here is the true strangeness of that first hour. The night side of the planet remains asleep. East of the Terminator, where it is evening or night, people rest in their beds, unaware. The darkness that has fallen on the day side is not particularly dramatic to someone lying in bed in darkness already. A person in their home in Tokyo or Hong Kong, in the middle of what should be their night, feels no immediate change. They sleep on while, thousands of kilometers to the west, the daytime world is rewriting itself into horror. The psychological experience of those first minutes is perhaps the most difficult to imagine. Consider the visceral and evolutionary weight of sunlight. For hundreds of thousands of years, human beings have relied on the sun's presence to mark time, to signal safety, to regulate the deepest rhythms of their bodies. A sudden, complete absence of daylight, during the hours when daylight should be brightest, triggers something ancient and difficult to quantify. It is not simple fear. It is something closer to a fundamental wrongness in the structure of the world itself. As that first hour progresses, more and more of the globe tumbles into this darkness. The Terminator line continues its eternal rotation, and people living in the band of Earth's surface where it is day watch the light drain from their skies. It spreads outward from that first moment of cessation, a wave of impossible darkness racing across the planet at the speed of Earth's rotation, roughly 1,000 kilometers per hour at the equator, much slower toward the poles. From New York, it would reach London in less than an hour. From London, it would reach Istanbul by the end of that first 60 minutes. Moscow would enter true sunless afternoon before the hour was complete. In those first moments, in cities and towns and farms, in cars and airplanes and ships, people would begin to react. What starts as confusion would shift towards something more urgent. Some would turn on lights. Streetlights flicker on across cities in the middle of what should be bright day. Traffic lights continue their regulated cycles, meaningless now, casting their red and green light into a darkness that should not exist. Airports and air traffic control centers would begin to receive reports from hundreds of aircraft simultaneously, all describing the same impossible phenomenon. The sky, in daylight altitudes, has become night. The stars are appearing overhead, bright and clear, shining down on a world that should still be lit by the sun. That first hour is the hour of disbelief, really. It is the hour in which people's minds are still catching up to what their senses are reporting. The darkness is not total. City lights, artificial lights in buildings, headlights and street lamps begin to illuminate parts of the dayside, but the absence of the sun's light is total and undeniable. The sun, our constant and unquestioned companion, has vanished, and the hour moves onward, carrying darkness with it around the spinning world. In that first bewildering hour after the sun's light ceases to reach us, something extraordinary and deeply unsettling unfolds across the lit hemisphere of Earth. The darkness doesn't arrive all at once in a kind of cosmic switch. Instead, it deepens. The sun's fading light, already extinguished 8 minutes earlier in the furnace of space, begins its final descent across our daylit world. Those standing in daylight at the moment of the solar extinction wouldn't notice immediately. A few more minutes would pass. Birds in flight would continue their trajectories. Office workers would stay bent over desks. The sky would remain, moment by moment, subtly less bright than it was before, like the opening of an eclipse, but without the moon's silhouette creeping across it. Instead, there would only be dimming. The quality of light would shift, cooling from gold to grey, and then, gradually, inexorably, the strange darkness would deepen. Within perhaps 10 or 15 minutes of true solar failure, the change would become unmistakable. The sun hanging in the sky would grow visibly fainter. The world would notice. It would know something ancient and essential was ending. Shadows would begin to sharpen and lengthen in ways that seem impossible at midday. The quality of light would become strange, neither night nor day, but something in between, something wrong. And then, perhaps half an hour after the moment of darkening, something remarkable would occur across the daytime sky. The stars would begin to appear, not gradually, as they do at dusk, but steadily, becoming visible in increasing numbers. Sirius, Canopus, Procyon. The planets too, Jupiter hanging visible even in the remaining twilight, Venus emerging like a ghost. The constellation Orion, upright and clear in a sky that still held a bruised purple glow along what had been the sun's location. It would be beautiful and horrifying in equal measure. The sight of the stars during what should be afternoon would strike human consciousness like nothing in recorded history. We would see simultaneously what the universe actually looks like, that the night sky we know is not a nightly oddity, but the true state of things. The stars are always there. We simply cannot see them, because our star drowns them out with its overwhelming light. What kind of sensory disorientation would this produce? Imagine standing outside at what your body insists should be 2 p.m., your circadian rhythm still expecting warmth and brightness, and instead finding a sky full of stars. Your pupils would dilate rapidly. Your eyes would sting as if adjusting to sudden dimness after emerging from a dark room. The ambient light around you would be enough to see by, a strange, silvery twilight cast by the starlight itself, by the reflected light of the planets, by the faint glow of distant galaxies becoming barely visible. You would be able to move about, to see your hands, to recognize the features of the landscape around you. But it would be like seeing the world through a gauze of ink. The colors would drain from everything. The grass would become grey-green. The buildings would lose their warm undertones and appear almost monochromatic. The sky itself would be the deepest, most penetrating blue-black, not the black of night, but something between, like the color just before true darkness falls on a clear night after sunset. It would be neither day nor night, but a third thing entirely. The psychological impact of this moment, and it would be a moment that stretched into hours before settling into days, would be profound and difficult to overstate. Human consciousness has evolved over millions of years in the presence of a sun. Our biology expects it. Our minds have no category for this. There would be a kind of cognitive vertigo as the brain tried to process contradictory signals. The angle of the light says it is midday, but the darkness says it is night. The watch says 2 p.m., but every cell in the body is beginning to receive signals suggesting something is terribly wrong. The world would fall silent. Not immediately, and not everywhere, but the quality of sound itself would change. Birds, many of which depend on light levels to determine when to sing and when to rest, would fall quiet. Their sudden silence would add to the eeriness of the day. The insects would begin their evening songs, though the sky would still hold the light of the star-filled darkness. Dogs would become confused, their routines thrown into chaos. Humans would pause in their work. Traffic would slow as drivers noticed the strange light. And then, gradually, the realization would begin to spread. The world had not ended, not yet, but something irrevocable had changed. The sun had failed. The source of all warmth, all light, all life on earth had gone dark, and in that realization there would be a kind of existential quietness that would fall over the planet like snow, a silence more profound than the absence of sound, a silence of certainty replaced by profound uncertainty. In those first hours after the sun's sudden absence, while the night side of Earth continues its ordinary sleep and the day side grapples with shock, something far more fundamental has already begun. The atmosphere you breathe, the waters that cover most of your world, the soil beneath every growing thing, they are all, quite literally, beginning to cool. Not slowly, not gently, but with a speed that would have no precedent in the modern human experience. The sun's energy does not linger in the way we might hope. It radiates outward in all directions, and what reaches Earth has already traveled 93 million miles to arrive. Once that journey ends, the light that strikes the dayside during those first bright hours is the last light that will reach the planet for some time. And as that final sunrise rays fade into the hours of darkness, the radiative balance that has held steady for billions of years begins to tip in only one direction, away. Within the first few hours of darkness, the temperature on the illuminated side of Earth begins its descent. Not dramatically at first, but measurably. The asphalt of a city street, which may have climbed to 120 degrees in the summer sun, begins to cool. So too does the dark soil of a field. The ocean's surface, that vast heat sink that has absorbed the sun's energy throughout the morning and early afternoon, stops receiving new warmth and begins to radiate what it holds into an indifferent sky. The rate of cooling depends on what lies beneath. Dark surfaces cool faster than light ones. Land cools faster than water. Humid air over the oceans slows the process slightly, while the dry interior of a continent experiences steeper drops. By the end of the first day, as the rotating Earth carries the initial darkness across the equator and toward the poles, global temperatures have begun falling in earnest. The day side, now fully night, has lost perhaps 10 to 20 degrees Fahrenheit from where it began, depending on latitude and local conditions. In some places, more. In others, slightly less. But everywhere, the trend is the same. The thermal energy that the sun deposited over months and years is now being shed into space, radiated away into the vacuum as infrared heat, never to return. The ocean surface behaves differently than land, and this matters profoundly for what comes next. Water has an enormous heat capacity. It takes far more energy to raise or lower its temperature than it does for soil or air. A vast ocean absorbs solar radiation throughout its surface layers, storing that warmth in the water itself. In the first day of darkness, the sea surface temperature begins to fall, but only slowly at first. The upper meter or so of seawater might cool by just a few degrees in those first 24 hours. Deeper waters, which have been accumulating heat from seasons and years of sunlight, remain warm, still insulated by the layers above them. This thermal inertia is one of the last kindnesses our planet possesses in this scenario. But the air above the water cools far more rapidly. The atmosphere does not store heat the way the oceans do. It responds almost immediately to the loss of solar radiation. Within hours, the air temperature above the dayside begins to plummet. Wind patterns, driven by the temperature differences between equator and poles, begin to shift. The convection currents that normally carry warm air upward from the heated surface become sluggish. Cold air begins to settle. By the end of the first day, the temperature in many populated regions has fallen by 30 degrees or more. This is the moment when the true vulnerability of our biosphere begins to reveal itself. Not in the darkness itself, which is shocking but survivable in the short term, but in the cold. The sun is not merely a source of light. It is the fundamental engine that drives the temperature at which all life has evolved. A temperate zone at 60 degrees Fahrenheit is suddenly on its way to 40. The tropics, which have never in recorded history experienced frost, are moving toward temperatures they have no genetic memory of. Plants begin to sense this change through mechanisms we are only beginning to understand. Shifts in moisture, changes in air pressure, the loss of the familiar spectrum of light that has guided their growth. The ground itself, having absorbed the sun's warmth throughout the growing season, acts as a slowly releasing reservoir of that energy. In the first day, soil temperature falls, but the deeper layers, particularly in places where the ground was already warm, continue to release stored heat upward into the frigid air. This delay creates a brief window where the temperature gradient is inverted in unexpected ways. Cold air sits above warmer ground, creating weather patterns that seem chaotic. Dense fog, strange wind shears, the sensation of the atmosphere becoming unstable. And still, most of the planet's population sleeps through this gradual transformation. On the night side, where the sun has not yet failed to rise, the temperature has already begun to respond not to the sudden absence thousands of miles away, but to the shift in atmospheric circulation triggered by the extreme cold on the day side. Warm air from the night side rushes toward the cooling day side, creating powerful winds and pressure systems that begin to reshape the planet's weather almost immediately. These are not gentle zephyrs, but genuine atmospheric rivers of displaced air, moving because the temperature difference between day and night has become more extreme than it has ever been. By the end of that first day, the planetary temperature has dropped perhaps 15 to 30 degrees on average, with far more extreme variations in different locations. Ice that has not formed in certain regions for centuries begins to nucleate on surfaces. Morning frost appears in the subtropics. The permafrost in the far north, which has been retreating for decades, suddenly begins its expansion again, hardening within hours. And in the oceans, where the cooling is more subtle but no less relentless, the surface waters are beginning to lose their equilibrium. Evaporation slows dramatically as the air above the water becomes cold enough to hold less moisture. The hydrological cycle, that fundamental engine of weather and climate, begins to stutter. The birds notice first, perhaps. Those creatures whose metabolism burns hot and fast begin to sense the encroaching cold within hours. The insects, so dependent on the warmth of the sun, slow their movements as their body temperatures match the cooling air. And somewhere in the deep, ancient parts of the human brain, in the portions that still remember when our ancestors huddled around fires in an endless night, something stirs. A recognition, not yet conscious, that the world is becoming hostile to all the life that has taken for granted the sun's eternal presence above the horizon. Within the first few days of this theoretical darkness, something far more fundamental than temperature begins to unravel. The processes that built the world as we know it, the silent, invisible transactions that move energy from light into life itself, would simply cease. Across every ecosystem on Earth, in gardens and forests and the sun-drenched oceans, photosynthesis would stop. Consider for a moment what photosynthesis truly is. It is not merely plants absorbing sunlight. It is a quantum-level dance. Molecules catching individual photons and using that captured light energy to split water, to fix carbon, to build the sugars and compounds that literally become the flesh and bone of every living thing. Every breath you've ever taken, every apple, every fish, every blade of grass, they are all built from ancient sunlight, transformed by this one elegant process. Without photosynthesis, that pipeline of energy collapses entirely. In a world without the sun's light, the first casualties would be the plants themselves. Within days, not weeks, the green leaves hanging from trees across the globe would begin a quiet decline. Trees and shrubs, having lost their primary fuel source, would shut down their growth processes almost immediately. The chlorophyll that makes them green would cease its work. But the plants would not simply fall over dead. No, the process would be more like watching a battery drain. They would continue to consume their stored reserves of starches and sugars, slowly burning through the energy they had accumulated in brighter times, until those reserves too were exhausted. A mature oak tree might survive several weeks on stored energy alone. A seedling would last days, perhaps a week at most. The ocean's response would be even more dramatic, and perhaps more consequential. In the euphotic zone, that sunlit upper layer where light can still penetrate, live the phytoplankton. These microscopic organisms, diatoms and dinoflagellates and cyanobacteria, form the base of nearly every marine food web. They are, in many ways, far more important to the survival of ocean life than all the fish combined. When sunlight vanished, phytoplankton would begin to fail within days. Some species might linger slightly longer than others, consuming their internal reserves or relying on whatever faint ambient light remained in that first week. But by the end of a week, perhaps two at most, the phytoplankton bloom that usually colors vast stretches of ocean would thin dramatically. The water, where it had been clouded with life, would begin to clear, not because the ocean was becoming cleaner, but because the living base of its food web was quietly dying. What happens next is a kind of cascading unraveling, a gentle but inexorable collapse through the layers of the food web. The zooplankton, tiny creatures that feed on phytoplankton, would find themselves without food. These microscopic herbivores would begin to starve almost immediately. Some might survive a few weeks on their internal fat reserves, but with no new photosynthetic energy entering the system, this could only ever be a temporary reprieve. Within days to weeks, zooplankton populations would plummet. And so the predators that depend on zooplankton, the small fish, the larval stages of larger fish, the filter feeders, would themselves begin to starve. Have you ever thought about how quickly a food web can fracture once the foundation is gone? It is not necessarily a violent collapse. It is more like a structure losing its foundation one support beam at a time. The system doesn't explode. It quietly, systematically, stops working. On land, this unraveling would follow slightly different timelines, but the pattern would be the same. Herbivorous insects would find leaves that no longer had the energy to maintain their tissues, leaves that were slowly being consumed by the plant itself as it burned through reserves. Within the first week or two, populations of grasshoppers, caterpillars, aphids, and the countless other insects that depend on living plants would begin to decline, and with them would go the birds, the insectivores first, followed by granivores as seeds became scarce when plants failed to complete their reproductive cycles. In temperate forests and grasslands, the herbivores, the deer and elk and rabbits that browse on vegetation, would continue to eat for a time, but the plants themselves would be dying, becoming less nutritious and less accessible as growth stopped and tissues began to break down. Within 2 or 3 weeks, vegetation that still appeared green on the surface would be failing at the cellular level, unable to repair itself, unable to produce new growth. The food that had seemed abundant would become increasingly deficient in nutrients and energy. What emerges from these first critical days is a profound insight. The food web is not a web at all, in the sense of an interconnected mesh that can function in multiple ways. It is more like a tower built on a single pillar. Remove the light, remove the photosynthesis that transforms sunlight into sugar, and you have not simply disrupted one link in the chain. You have severed the source. Everything else in the system is downstream from that original transformation, utterly dependent on a flow of energy that has now stopped. The cracks in the system would become visible quite quickly to anyone who was watching, though in this scenario, most would be preoccupied with far more immediate concerns like finding light and fighting the cold. But if one had the detachment to observe, one would notice within the first 2 weeks that the world was beginning to look different. Fewer insects at dusk, fewer birds at dawn, the plants losing their vigor more rapidly than temperature alone could explain. It would be, in a sense, a preview of a much darker transformation still to come, the transformation of a living world into something far more austere and desperate. Yet in these early days much would still remain. The decomposers, fungi, bacteria, would still have work to do, still have the bodies of dying organisms to process. Scavengers would still find meals in the corpses of creatures that had starved or simply given up. For a brief window, perhaps 2 to 4 weeks, there would still be pockets of life, still be the echoes of the old systems struggling to function. But the trajectory would be clear to anything capable of understanding it. The foundation had been removed, and what remained was simply a temporary holding pattern before the final silence. As the days unfold in darkness, something far quieter than the physical cold begins to reshape the living world, a cascade of collapse, so gradual that individual moments might seem unremarkable, yet together they sketch the unraveling of nearly every ecosystem on Earth. By the end of the first week, the insects have begun to vanish. Bees, moths, and butterflies, creatures whose bodies carry no internal furnace of their own, grow sluggish as external temperatures plummet. They cannot regulate their core heat like mammals or birds, and without the sun's warmth to activate their muscles, their behavior becomes fragmented, disoriented. Some seek shelter in the soil, under bark, within the last remnants of decaying vegetation, but shelter itself becomes colder each passing day. The crickets that once sang through summer nights fall silent. The beetles that crawled through forest floors grow immobile, on leaves now stiffening with frost. And yet, in those first few weeks, it is the absence of light that kills more swiftly than the cold alone ever could. Photosynthesis, the quiet engine that has fed nearly every living thing since the sun's earliest light touched our planet, has simply stopped. Plants are still alive in their cells, their cellular machinery intact, but they are no longer feeding. The vast fields of wheat and corn across every continent stand green but hollow, their leaves still present but drawing no energy from light. In the oceans, the phytoplankton, Those microscopic ancestors of every fish, whale, and seabird cease their frantic multiplication. The blooms that painted entire seas with color and life have begun to fade. The foundation of almost every food chain, from the tiniest copepod to the greatest whale, has vanished. Within 2 weeks, the herbivores, the grazing animals that depend entirely on plants, face an impossible choice with no solution. Deer browse through meadows of leafless grass. Rabbits nibble at bark and woody stems, but these cannot sustain them for long. Insects that fed on plant nectar and pollen find neither. The birds that hunted insects begin to starve. Sparrows, finches, robins, birds that nested in spring with hopes of summer abundance find themselves in a lightless, frozen world where no insects emerge to feed their young. Do you wonder what those first mornings must feel like for creatures wired by millions of years of evolution to expect dawn? The forests, those ancient cathedrals of growth and complexity, begin their own slow dissolution. The trees themselves, though they are still alive in their roots and trunks, cease to photosynthesize. They draw only on the reserves of energy stored in their wood and root systems, energy meant to last them through winter until the spring sun would return. But the spring never comes. Week by week, that stored energy runs thin. The deciduous trees that have already shed their leaves stand bare against a starless sky. The evergreens hold their needles, but there is no light to feed them. They remain alive for weeks, perhaps months, but they are dying in a manner almost invisible to the eye. The forest floor, normally a rich tapestry of decomposition and renewal, begins to transform. The fungi that break down fallen wood and return nutrients to the soil are themselves slowing. They are not plants, but they too depend on the energy that ultimately flowed from sunlight, captured by the plants whose remains they consume. Earthworms, which once worked through millions of tons of soil daily, burrow deeper into the earth seeking the faintest residual warmth. They too are consuming their own reserves, unable to find new food. In the rivers and lakes, a different tragedy unfolds. The small fish and fish larvae that feed on phytoplankton have no food. The zooplankton that once grazed on the endless pastures of algae bloom are starving. Freshwater plants, water lilies, cattails, pondweeds, have stopped producing oxygen. The water itself, still liquid in the first weeks but growing colder, becomes darker and colder and emptier. The larger fish, predators that once moved freely through these waters, begin to find their smaller prey simply gone. Some fish attempt to slow their metabolism dramatically, entering a state of torpor not unlike hibernation, but it is a survival mechanism meant for weeks or months, not for indefinite darkness. By the 3rd and 4th week, the visible animal life in temperate and tropical regions has diminished strikingly. Bird populations that once numbered in the millions now shelter in caves and hollows, many already succumbing to cold and hunger. The insects, those teeming multitudes that once filled the night air and the day, are, as a collective, nearly gone from the surface. Grasshoppers have vanished. Dragonflies no longer hunt over ponds. The bats that pursued them in darkness have begun to emerge and hunt desperately for any flying insect they can find. But there is almost nothing to hunt. Think about what this means for the creatures that depend on abundance. A swallow once caught hundreds of insects in a single day. Now there are no insects. A spider web, once a miracle of engineering capturing dozens of prey, now hangs empty day after day. The silent ecosystem does not fall all at once, like a tree felled by an axe, but rather it folds inward, one link at a time, one species at a time, each starvation triggering another, each absence creating a new vacuum. The forests of the tropics, which have never experienced such profound cold and darkness, begin to show strain that would be invisible to our eyes, but is happening nonetheless. The orchids, the bromeliads, the countless plants adapted to constant warmth and light, are in shock. Many will simply die in place, their cells crystallizing as temperatures drop far below what they have any mechanism to survive. The monkeys, sloths, and birds of tropical canopies have no hibernation instinct, no stored fat for a long winter, and there is no food for them in this darkened forest. The ocean, vast and seemingly infinite, is experiencing its own slow collapse, though one that will take longer to become visible. The phytoplankton, having ceased reproduction, are being consumed by the zooplankton, still alive and hunting, but this is a one-way street. The plankton populations are crashing. The small fish species that feed on plankton begin to starve within the second and third week. The sardines that school in millions find their food source shrinking precipitously. The larger predatory fish, tuna, sharks, groupers, still have their smaller prey, but for how long? The food web, that intricate network of who eats whom, is unraveling from the base upward, and it is a process that will take weeks to make itself fully apparent, but has already begun in irreversible earnest. Is there something almost merciful in this gradual nature of collapse, rather than a sudden extinction? Or is the slow starvation somehow more tragic, more layered in its suffering? Perhaps we might consider it a matter of perspective we cannot fully own, observing as we do from a place where the sun still shines, at least in our thoughts. By the fourth week, a quietness has settled over the natural world that is almost unbearable in its depth. The birds have largely vanished, either dead, or in a few cases, those hardy species with reserves of fat and instincts for survival huddling in whatever shelter they can find. The forests stand increasingly empty. The sound of insects, that constant background hum of life that has filled every night and many days since evolution first created wings, has been nearly erased. In its place is silence, the silence of a living world that is, very slowly, ceasing to live. Meanwhile, beneath the darkening sky, the vast infrastructure that sustains our civilization begins to feel the weight of a cold that has no precedent in living memory. The power grids that hum across continents, those intricate networks of transmission lines and transformers that have grown accustomed to a certain rhythm of demand, now face something they were never designed to weather. As temperatures plummet across the first weeks and into the first months, the need for heating becomes not a comfort, but a desperate necessity. Furnaces and heating systems that might serve a region through a typical winter now run without reprieve, drawing electricity from grids that themselves are struggling. Consider the cascade of failures that begin to unfold. Natural gas pipelines, which snake beneath cities and across territories, rely on careful pressure management. When the world grows cold beyond measure, the brittleness of metal increases. Welds that have held for decades become fragile. Pipelines crack. Storage facilities, designed with margins that suddenly seem quaint, deplete at rates no one predicted. Power plants themselves, whether fossil fuel or nuclear, require cooling water. Rivers and reservoirs begin to freeze. Nuclear facilities can operate in extreme cold, but the water systems that feed them grow unreliable. A few plants may shut down not from malfunction, but from the simple inability to cool their reactors safely. The blackouts begin, first rolling, then regional, then entire time zones plunge into darkness. This darkness compounds the crisis. Heating systems fail without electricity. Water treatment plants, which depend on constant electrical supply and stable temperatures, begin to falter. The pumps that move water through municipal systems grow sluggish as the substance itself approaches freezing in pipes and reservoirs. In the first month, cities face water shortages not because water doesn't exist, but because the systems that move it have become brittle and inefficient. Some pipes burst. The pressure drops, and in that pressure drop, contamination can seep in, a secondary catastrophe, layered atop the primary one. Agriculture, That vast global enterprise that feeds nearly 8 billion people stands paralyzed. The crops that remain in the soil have already failed. Livestock shelters, designed for ordinary winters, cannot maintain temperatures needed to keep animals alive. Farmers make impossible choices. Heating barns becomes economically ruinous when heating fuel itself is scarce and expensive. Some animals are slaughtered early out of mercy and necessity. Others simply perish in the cold. The grain stores in silos and warehouses become a precious resource, and suddenly the question of distribution, of ensuring that food reaches population centers before it spoils or runs out, becomes a matter of national mobilization. Transportation networks fracture under the strain. Trucks that move food and fuel find roads increasingly treacherous. Ice accumulates faster than it can be cleared. Fuel lines freeze in vehicles. Batteries, which power electric vehicles and provide emergency systems, lose efficiency dramatically in extreme cold. A car battery that might normally provide several hours of use may offer only minutes in temperatures of -30, -40, -50 degrees. Railway lines contract and warp as cold seeps deep into the metal and concrete. The global supply chain, already strained by the failure of photosynthesis and the collapse of ecosystems, now finds its physical arteries becoming unreliable. Water systems face a peculiar vulnerability. Municipal reservoirs begin to freeze from the surface downward, slowly. As they do, the ability to draw water from their depths becomes complicated. Ice dams form, treatment processes that rely on chemical reactions and biological processes slow dramatically in near-freezing conditions. Sewage systems, too, face a crisis. The bacteria that decompose waste cannot function in extreme cold. Septic systems and treatment plants become choked with partially processed waste. In rural areas, septic tanks freeze solid. In cities, sewage backs up into basements and streets. But perhaps most quietly devastating is the failure of supply chains for the very things needed to survive. Fuel delivery becomes erratic. Diesel fuel gels in extreme cold. It thickens, clogs filters, refuses to flow. Heating oil does the same. Natural gas remains gaseous, but the pipelines and infrastructure that deliver it are compromised. Medical supplies begin to dwindle. Hospitals, which consume enormous amounts of electricity and water, find themselves operating at reduced capacity, if they operate at all. Some generators fail. Some fuel deliveries never arrive. Across the first months, a kind of creeping paralysis settles over human civilization. Not a sudden collapse into chaos, but a gradual seizing of the complex machinery that supports modern life. Power outages extend from hours into days. Water becomes intermittent. Food distribution becomes sporadic and localized. Communication networks degrade as power fails at cell towers and data centers. People find themselves increasingly isolated, not always from neighbors, but from the wider structures of civilization that they had come to assume were permanent and reliable. And underneath all of this, the temperature continues to fall, not as rapidly as the first shocking weeks, but steadily, relentlessly. 60 degrees below zero, 80 degrees below zero. The world is entering a phase of deep cold that has no historical parallel in human experience. As the darkness deepens across those first weeks and months, something profound begins to shift in the very fabric of Earth's atmosphere itself. The air that once carried warmth from the sun in every direction now becomes a medium for loss rather than gain, and the atmosphere begins to behave in ways that would seem almost alien to anyone who had ever witnessed our planet's weather before. The temperature of the troposphere, that lowest layer where we live and breathe, continues its relentless descent, falling further with each passing day, and as it does, the composition of the air itself begins to change in subtle but consequential ways. Water vapor, which once rose freely from the oceans and forests to form clouds and weather patterns across the globe, begins to condense more readily as temperatures plummet. The air becomes drier in some regions and paradoxically wetter in others, as the delicate balance between evaporation and condensation tips toward precipitation. You might imagine precipitation falling not as rain or even as snow now, but as a strange mixture of both, sleet and freezing rain accumulating on every surface, on the abandoned buildings and the barren fields, layer upon layer of ice, forming a crystalline coat over the landscape. The wind patterns that once carried heat from the equator toward the poles begin to slow and shift, no longer driven by the temperature differential that the sun had so carefully maintained. The atmosphere becomes more sluggish, less dynamic, and in that sluggishness there is a kind of quiet resignation to the new order. The oceans, meanwhile, are engaged in their own gradual transformation. The surface waters begin to freeze, particularly in the polar regions, where the sea ice that once melted with each passing summer now becomes permanent. The process is slow at first, layers of fragile ice forming on the surface, those delicate, needle-like crystals of frozen water that give the sea the appearance of having become viscous, almost oil-like. But as the weeks turn into months, a true sheet of ice begins to form. The freezing point of seawater is slightly lower than that of fresh water, around -2 degrees Celsius, because of the salt dissolved within it. But with air temperatures falling to tens of degrees below zero, even the salt-laden oceans begin to surrender to the cold. The ice thickens slowly but persistently, insulating the water below from the increasingly frigid air above, creating a kind of thermal buffer that slows the transfer of heat away from the deep ocean. And here lies something almost paradoxical, something that speaks to the slow patience of thermal dynamics. Deep beneath the ice, far below the sunlit surface where photosynthesis once bloomed with abundance, the ocean retains heat. The deep currents, those great rivers of water that circle the globe, carrying warmth from the equator toward the poles and cold from the poles back toward the equator, still hold the memory of days when the sun shone upon them. The thermal inertia of the ocean, the vast energy stored in the warmth of its depths, means that while the surface freezes and the shallow waters cool dramatically, the deep ocean remains relatively warm, at least by comparison. This is not comfort, you understand, but merely the lingering momentum of a world that has not yet fully adjusted to its new reality. The temperature of the abyssal depths, those cold regions already near freezing even in our present world, begins to cool fractionally, but the change takes months, even years, because heat travels slowly through water. The result is a kind of vertical stratification that would have been familiar to any oceanographer, but now inverted in its meaning. The surface waters, locked in ice, become isolated from the atmosphere above. The shallow waters below them cool steadily but lag behind, and the deep waters, for now, remain refuges of relative warmth, pockets of energy in an increasingly cold world. This layering creates profound implications for ocean circulation. The thermohaline circulation, that great conveyor belt of water that depends partly on temperature differences to drive its flow, begins to weaken. In our present world, cold, salty water sinks near the poles, and warm water rises near the equator, creating a circulation that has persisted for millions of years. But without the sun's input, without the constant heating of the surface waters in tropical regions, this system falters and stalls. The atmosphere, meanwhile, continues to cool at an accelerating pace, not because temperatures are falling faster, but because the mechanisms that would restore warmth have vanished. The Earth still radiates heat that accumulated over billions of years, still has some internal warmth from radioactive decay in the core, but it is like a campfire that has burned through its fuel. There is still warmth in the ashes, but less with each passing hour. The upper atmosphere, the stratosphere, and beyond, experiences a particularly dramatic change. Without solar radiation to heat it from above, the stratosphere becomes colder still, and the temperature gradient that normally exists, where the troposphere is colder at its upper reaches and warmer below, begins to invert further. The air becomes more stable in some ways, less prone to convection and storm formation, because there is no longer a heat source below to drive updrafts and cyclones. Oxygen levels in the atmosphere remain relatively stable at first, since it is photosynthesis that has failed, not respiration. The oxygen produced over billions of years remains in the air, but its abundance becomes almost meaningless, as the living systems that depend on both oxygen and the products of photosynthesis begin to collapse. The atmosphere, paradoxically, becomes both more stagnant and more transparent. Without the water vapor and clouds that once reflected and scattered sunlight, the sky becomes clearer, but also emptier. The stars visible now in a way they have not been seen since before dawn, visible even at midday in some locations as the sky darkens to a deep indigo, then grey, then nearly black. Consider the irony of it. The atmosphere that once worked tirelessly to distribute the sun's warmth across the planet, creating the weather systems and wind patterns and gentle breezes that we took for granted, now becomes a medium for uniform cooling. The energy that once flowed through it in great spiraling patterns now dissipates more quickly, leaking away into space. And beneath all of this, the oceans hold on to their warmth like a memory, slowly releasing it to a world that no longer has any source of replenishment. For a time, weeks, months, perhaps a year or two, the deep ocean remains a pocket of relative stability, a dark and cold repository of thermal energy that will eventually, inexorably, follow the rest of the planet into a new equilibrium. And as Earth's surface grows colder by the hour, something far more subtle and equally profound begins to unfold in the invisible realm above our heads. The sun, even in its violent fusion, does more than simply radiate light and heat downward. It sends forth a constant stream of charged particles, a wind, as astronomers call it, a thin but persistent exhalation of plasma that flows outward through the solar system at speeds approaching 400 miles per second. This solar wind has been pressing against Earth's magnetosphere for billions of years, shaping it, defining it, holding it in a delicate shape like water flowing around a stone. The magnetosphere itself is one of Earth's most elegant and invisible guardians. Born from the iron that churns in our planet's outer core, this magnetic field extends far into space, creating a protective bubble that deflects the sun's charged particles away from our atmosphere. It is not a wall, it is more like a river's current, bending around an obstacle, creating eddies and flows and hidden channels. And for the entire history of complex life on Earth, this shield has been standing watch, preventing the solar wind from slowly stripping away our atmosphere, from bombarding our DNA with radiation, from making the upper reaches of our sky a place of constant, lethal particle flux. When the sun goes dark, the solar wind does not simply vanish in an instant. What ends is the heating mechanism that drives that wind, the magnetic tension that accelerates those particles outward. The plasma that has already left the sun, the wind already in flight, will continue its journey for some time, carrying its last messages across the void. But gradually, hour by hour, that wind will thin and weaken. The pressure it exerts on Earth's magnetosphere will begin to diminish. Imagine a hand that has been pushing steadily against a door for so long that you have forgotten the hand was even there. Then the hand relaxes. The door does not immediately swing closed. The hinge does not suddenly creak, but the tension changes. the geometry of the barrier itself begins to shift in ways that are almost imperceptible at first, and yet profound in their implications. This is what happens to Earth's magnetosphere as the solar wind fades. The field does not collapse. It is anchored deep within the planet, rooted in the motion of molten iron kilometers below our feet, but without the dynamic pressure of the solar wind pushing against it from without. The shape of the field begins to change. It compresses on the day side, the side facing the dying sun, and extends farther on the night side, as if the shield is no longer being held in its familiar teardrop configuration, but is beginning to drape and settle into a new, quieter geometry. And here, in this subtle shift, one of Earth's most visible wonders begins to fade. The aurora, those undulating curtains of green and red and violet light that dance across the polar skies, are born from the interaction of solar wind particles with Earth's magnetosphere. When those charged particles strike our magnetic field, they are guided downward along field lines toward the poles, and as they collide with oxygen and nitrogen molecules in the upper atmosphere, they release their energy as light. The aurora is Earth's response to being buffeted by the sun. It is a kind of celestial conversation written in radiance. As the solar wind weakens and the magnetosphere relaxes, the conditions that create auroras begin to fade. The displays that shimmer across northern Canada and Scandinavia and Alaska and the northern reaches of every high-latitude region, those green dances that have captivated humans since our species first looked upward, would gradually dim. They would not vanish utterly, not immediately. Some glow might persist, sustained by the last wisps of solar wind still arriving from the direction of the sun, but the brightness would diminish night after night. The frequency of storms would decrease. Within days, they would become rare, then rarer still, until the night sky above the poles would hold only stars and darkness, empty of that particular magic. But the auroras are, in some sense, a small consequence of a much larger shift. The loss of solar wind pressure means that Earth's magnetosphere is no longer being continually energized and disturbed by the impact of charged particles. The field would settle into something closer to a static state, no longer rippling with waves and instabilities. The radiation belts that surround Earth, those regions where particles become trapped and spiral along the field lines, would begin to lose their dynamic structure. Without new particles arriving from the sun to replenish them, those belts would gradually decay. This raises a question that carries some uncertainty, some gentle speculation woven through the physics. Without the solar wind to maintain a dynamic, disturbed magnetosphere, would the field itself begin to weaken? There are processes that suggest it might. The solar wind does not merely press against the field, it interacts with it in complex ways that actually help to sustain and regenerate it. Some of that energy feeds back into the system, helping to maintain the field's strength. The precise nature of this feedback remains an area where scientists still refine their understanding, where computer models offer varying predictions. It is possible that over longer timescales, weeks, months, years, the absence of solar wind interaction might allow the magnetosphere to gradually lose intensity. Such a loss would be slow. The Earth's magnetic field is anchored in planetary-scale forces that will not vanish quickly, but the protective layer that shields our upper atmosphere from direct particle bombardment would become thinner, more permeable. The radiation environment above the clouds would slowly become harsher. Those organisms living in the uppermost layers of the atmosphere, those hardy microbes and spores that ride the winds in the mesosphere, would begin to experience levels of radiation that current Earth-based life has evolved not to encounter. The rest of the planet, huddled in the growing cold, would not feel this change directly. The magnetosphere's weakness would not warm the air or slow the spreading ice, but it would represent a subtle erosion of one of the systems that has made Earth habitable for so long. The shield would be thinning. The invisible hand that has held back the cosmic wind would be releasing its grip. Yet this sudden extinction we've been imagining, this instant snuffing of the sun's light, bears almost no resemblance to what the sun will actually become, and understanding that difference softens something in us, perhaps, because the true ending of our star, the one written into the physics of stellar evolution itself, unfolds not in minutes or hours, but across timescales so vast they dwarf human comprehension entirely. The sun, as it exists now, has perhaps 5 billion years remaining, not 5,000, not even 500,000. 5 billion years of continued burning, of steady fusion in its core, of light streaming toward Earth with the same quiet reliability that has shaped every moment of life's history. This is not a problem that humanity, or even the species that might succeed us, will face in any imaginable near future. The number itself becomes almost abstract when we contemplate it. To put it another way, the sun has already burned for 4.5 billion years, and it will burn for another billion years longer than it has already existed. That is the scale we are discussing. But what happens when that fuel, finally, begins to truly run down? The process begins not with darkness, but with brightness. The sun, you see, does not simply fade. Instead, as its core becomes a denser and denser sphere of helium, the ash, left behind by hydrogen fusion, the gravitational pressure intensifies. The core contracts while becoming hotter, reaching temperatures high enough to ignite a new reaction, helium fusing into carbon and oxygen. This new fusion generates tremendous outward pressure, and the sun's outer layers expand, dramatically, catastrophically, from a certain perspective. The sun will swell into what astronomers call a red giant. Its surface will cool somewhat, becoming orange and reddish rather than the bright white yellow we know. But this cooling of the surface is accompanied by an enormous increase in total luminosity. The star becomes brighter overall, even as it grows dimmer in the blue wavelengths of light. Imagine a balloon being inflated to monstrous proportions, its surface stretching thinner and cooler, yet its total light output increasing because of the sheer volume of hot material radiating outward. The sun, in this phase, will grow large enough to swallow Mercury. Perhaps Venus. Some models suggest its outer atmosphere might reach Earth's orbit itself. This is not speculation in the sense of uncertainty. This is the well-established trajectory of stellar evolution, written into the equations of astrophysics and confirmed by observations of countless other stars at various stages of their lives. We can see red giants scattered throughout the sky, Betelgeuse, Aldebaran, others, and their properties align precisely with our mathematical models. The sun will join them. It simply has not yet. But here is what matters for this thought experiment we have been traveling through together. The transition to red giant status will take place over millions of years, not hours. The expansion will be gradual enough that it could theoretically be observed, tracked, predicted. There would be time, vast stretches of time, for life on Earth to respond, to adapt, to flee, or to simply end through the slow cooking of the planet's surface. The darkness we imagined, that sudden and absolute darkness that arrived 8 minutes after the sun went out, carries a violence and immediacy that the actual red giant phase will not possess. In a sense, the real ending of our star is far more merciful in its slowness and far more terrible in its inevitability. It is not an accident. It is not a catastrophe that strikes without warning. It is destiny, written into matter itself. The simple fact that stars exhaust their fuel and change, that nothing in the universe remains static, that even our sun, ancient and reliable as it seems, is only one moment in a vast and impersonal cosmic story. The red giant phase itself will last perhaps 2 billion years, an eternity by human standards, but merely a brief evening in the sun's much longer day. Eventually, after the helium in the core is spent, the outer layers of the sun will be shed, drifting outward to form what is called a planetary nebula, a beautiful cloud of glowing gas expanding into space. What remains will be the sun's core, now called a white dwarf, incredibly hot, incredibly dense, radiating away the last of its heat into the cold dark for trillions of years to come. This is the actual future that awaits our star, not the sudden silence and darkness of our imagination, but a slow, stately transformation, an aging, a gradual dimming and cooling across epochs that dwarf the entire span of human civilization. And knowing this, knowing that the true ending of the sun is so distant, so gradual, so utterly beyond the reach of any creature currently alive, or any whose existence we can reasonably predict, there is something almost comforting in it. The darkness we explored, the immediate and catastrophic darkness, exists only as a thought experiment. It is a tool for understanding what the sun means to us, for feeling the weight of our dependence on its light, for appreciating the fragility of the systems that sustain us. But it is not a threat we face. We face only the sun's slow aging, and that is something we need not fear for billions of years yet. There is time. There is always more time than we imagine. And yet, if we pull away from this particular darkness, from this imagined failure of our own familiar furnace, we find ourselves drifting outward into a cosmos where the ending of stars is not speculation but routine. Stars go dark constantly across the galaxy, though almost never in the gentle dimming we have imagined here. The universe has written many different endings for its light bearers, each one stranger and more violent than a simple, quiet fade. When a massive star, one perhaps 20 or 30 times the weight of our sun, exhausts its fuel, it does not slip away into a white dwarf's cold somnolence. Instead, something altogether more dramatic unfolds. The star collapses inward with sudden ferocity, and in that catastrophic compression, the outer layers are blasted outward in what we call a supernova, an explosion so violent that for a brief moment, that single dying star can outshine an entire galaxy of billions. Imagine that. One star, at the moment of its death, becomes momentarily brighter than countless others combined. And in that fury, in that irradiation of space, the light goes dark, not because the fuel simply ran out, but because the star has torn itself apart. The expanding shell of material dims over weeks and months, the brightness fading, until eventually only the memory of that tremendous flash remains in the electromagnetic record. Some of these supernovae leave behind a neutron star, a remnant so dense that a teaspoon of its matter would weigh as much as a mountain on Earth. And some of those neutron stars spin rapidly, throwing out beams of radiation like a cosmic lighthouse. We detect them as pulsars, and they too, though slowly, grow dimmer. Over billions of years, their rotation slows, their light weakens, and they fade into invisibility, becoming black holes sometimes, or simply cold cinders drifting through the dark. Other massive stars collapse not into neutron stars, but into black holes, and here the ending is perhaps more profound still. The star does not merely grow dark, it crosses an event horizon and effectively disappears from the observable universe, leaving behind only the ghost of its gravity, a void where light itself cannot escape. A star has not simply stopped burning, it has been erased, folded into the fabric of space-time itself. The more common story, though, is gentler. Most stars, including stars very much like our sun, will eventually become white dwarfs. And here we encounter something rather beautiful in its way. A white dwarf is not a dying star in the sense of collapse or explosion. It is a star that has already died, the core that remains after a sun-like star has shed its outer layers. And this white dwarf does not go dark immediately. Instead, it cools, extraordinarily slowly, across timescales so vast that not a single white dwarf created since the universe began has yet grown truly cold. In a sense, every white dwarf that has ever existed is still faintly warm, still radiating the residual heat of its long-extinguished fusion. Given enough time, far longer than the current age of the universe, white dwarfs would eventually cool to absolute darkness, becoming what we call black dwarfs. But none yet exist. The universe is simply too young for any star to have completed that final journey. When we look outward into the depths of space, we are looking backward into time, and we see stars at every stage of their endings. Some are detonating in supernovae, their death throes bright enough to be seen from across billions of light years. Others have already passed that violence and now sit as neutron stars, their surfaces crackling with trillion-degree magnetic fields. Others have surrendered entirely to gravity and vanished into black holes, and countless white dwarfs sit in the darkness, cooling infinitesimally slowly, waiting for an eternity that stretches beyond our comprehension. And there is something almost peaceful about observing this cosmic fact, is there not? That stars die in ways both violent and serene, that the light we see from distant supernovae has already happened, is already history when it reaches our eyes, that we are witnessing not danger, but the record of catastrophe long concluded. The massive star that exploded in what we now see as a brilliant flash was already gone when dinosaurs walked the earth. The remnant it left behind has been cooling and settling for millions of years. The light itself is the only thing reaching us now, a message from a distant past. It reminds us that the universe is vast not only in space but in time, and that even the most dramatic stellar endings unfold against a calendar so expansive that they seem, from our perspective, almost static. A supernova that burns for months in the Andromeda Galaxy is an ancient ruin from our vantage point in the Milky Way. The collapse of a star into a black hole is something that has already been swallowed by the universe, lost to the infinite past. And yet we still see them, still measure them, still sense their presence through the light and gravity they have left behind. Here, in this quieter meditation, we might notice how the endings of distant stars lend a certain perspective to our own sun's future. Whatever dramance awaits our star billions of years from now, whether it becomes a white dwarf or something stranger still, it is written in the nature of stars themselves. It is not unique suffering. It is the same story told across the galaxy, across all galaxies, wherever light has gathered in the form of a star and will eventually fade again. The diversity of stellar deaths, the beauty of their endings, suggests that there is something profound in the cycle itself, something almost comforting in the knowledge that our sun, too, will one day follow a path already traced by countless others. And in that wider cosmos, where stars go dark in ways both spectacular and serene, our imagined sudden darkness on Earth seems, in a strange way, less like a cosmic tragedy and more like a single moment in an endless progression of transformations, of matter returning to new configurations, of light yielding to dark, and dark waiting, always, for new light to be born again. And so we return, from the edges of that darkened world to the present moment, to the quiet fact that has held true across billions of years and across every human lifetime that has ever drawn breath on this planet. The sun has not gone dark. It continues to burn. In this very instant, as you listen to these words, atoms in that distant furnace are colliding, fusing, releasing the light that will reach your eyes in 8 minutes if you were to open them to a window. But perhaps you won't. Perhaps you're settling deeper into stillness instead, and that itself is a kind of grace. The thought experiment we've walked through, that hypothetical falling away of solar light, serves a purpose beyond the merely frightening. It teaches us, gently, what we might otherwise overlook in the everyday. That the sun's constancy is not inevitable, that its warmth and brightness, gifts we inherit each morning without payment and without ceremony, are the result of forces so vast and ancient that our minds struggle to hold them. 4.5 billion years of fusion. 4.5 billion years of the same patient transformation of hydrogen into helium, of mass converted into the energy that sustains every living thing, and it will continue for another 4.5 billion more, perhaps longer still, before the sun begins its slow transformation into something else, not a darkness, but a different kind of light entirely. A red giant dawn that is still, mercifully, incomprehensibly far away. When you think of the sun, really think of it not as a blazing ball in the sky, but as a presence, a companion, a fundamental condition of existence. Something settles in the mind, something like gratitude. Not the dramatic gratitude of catastrophe averted, but the quiet, tender gratitude of someone who has glimpsed, for a moment, how fragile the ordinary is, how easily it could be otherwise, and how precious it is that it is not. The sun rises tomorrow, as it has risen for billions of mornings before, as it will rise for billions of mornings hence. This reliability, this faithfulness, almost, if we may speak of stars in such terms, is woven into the fabric of consciousness itself. We have evolved in its light. Our eyes, our skin, our very sense of time and season and day are shaped by its rhythm. To imagine its absence is, in some way, to imagine the absence of ourselves. Yet here we are. The night sky above us, even now, holds more mysteries than the daytime ever could. Those distant stars that appear only when the sun's light has released its grip on the horizon, they are themselves suns, or remnants of suns, or newly kindled fires still learning to burn. The Milky Way spills across the darkness like a river, and somewhere within that river are worlds we will never see, lit by suns that may fail, may endure, may explode in supernovae, may collapse into white dwarfs no larger than the Earth. The universe is large enough to hold wonder and strangeness and endings. But here, for now, our sun persists. It burns. It sends its light across the void, and life drinks it in. And you, in this moment, are held within that light, even in the darkness of night, even in the stillness of sleep. You are cradled by the warmth that was generated millions of miles away. Heat that travels through the void as light, that warms the air you breathe, that is stored in the food you eat, that is woven into the very atoms of your body. The sun is not distant, for all its distance. It is intimate, it is here, and perhaps as you drift further into sleep, into the dream that awaits, you might notice that strange comfort, the knowledge that even now, even in the darkness, the light continues to journey toward you. 8 minutes of space separates you from its current state, but no time at all separates you from its effect. You are made of star stuff, as the saying goes, but more than that, you are made of sun stuff, of light transformed, of fusion continuing in the form of thought and breath and the quiet beating of your heart. Tomorrow, the sun will rise again, and the day after, and the day after that. For now, let that certainty be a pillow beneath your head. Let the thought of that steadfast, burning star millions of miles away be a song that carries you into sleep. It has not gone dark, and so the world, your world, continues. In the quiet dark of night, surrounded by the invisible warmth that even now is reaching toward you, you can rest, you can let go. The sun will be there when you wake.